We're now going to continue our demo and extract the topography data or bathymetry data that we're going to use for our realistic grid. So once again, this is I'm in the following directory ROMS grid, and I'm editing the script for the realistic topography. Now I'm going to scroll downwards, skipping the stuff that we already did, like building the grid file and so forth, up to the topography. Okay. So the first thing that I want to do is I want to set the topography of my grid to a constant value of 4,000 meters, just to initialize it to something. So once again, my grid, I load it like this, and now I'm going to set this. The next step is to choose the data that I'm going to use the bathymetric data that I want to use. In this case, you have two options. The first option is to use the Sandrill and Smith satellite-derived bathymetry. This is from space, the satellite Topex satellite. It's probably a resolution of about 30 kilometer on average, given the smoothing and so forth. And so you can use this routine to extract this topography, or alternatively, you can use the satellite from another, the topography for another satellite called the eTopo5. And so you have these two options. Now, of course, if you were to have your own bathymetric data, for example, from soundings and so forth, or even high resolution, you can use it, and all you need to do is really to just extract the longitude, latitudes, and the bathymetric data in an area that encompasses the grid that you want to interpolate to. So let's start with this first part. So to extract the Sandrill-Smith topography, I just use this topo_extract_h, and I give the coordinate of the grid file of our grid, the grd.lon_r and grd.lat_r. So I go here in my MATLAB window, I do that, and when I do that, it's going to generate a figure, which is here. And in this figure, you can see that you extracted on the square grid of the satellite grid, this topography, and you can see here the coast, approximately the coast of the Gulf of Alaska, negative depth here in the ocean, positive over land with the mountain ranges and so forth. So that's really good. And now we can plot on top of this the location of our model grid by using this RNT grid box function. We do that. So, and if I look at figure 1, now I have here in black the boundary of my grid, of my computational grid, and I use to plot this, I just use the function RNT grid box, the GRD, which is the structure of the grid, and then K, just to tell it that I want it to color K. So color black, K stands for black. If I wanted, for example, to use color red, I can do that, and it changes the color. So now we have, the next step is to interpolate from the satellite grid, which is this square grid over here, to the ocean ROMS grid, which is this one right here, which is curvilinear in that it follows the x and y's are in this directions and not in the north-south direction. Okay, so how do we do that? Well, there's a function here. It's called RNT grid data. This RNT grid data is a similar function of the MATLAB grid data, which is used to map two-dimensional data from one grid to the other. Grid data is just an improved version of that. And typically, you give the longitude and latitude of the field, in this case the topography field of the stuff that you have, in this case the satellite grid, and then you give the longitude and latitudes of the grid where you want to interpolate to. You also have to specify the type of interpolation. I selected cubic. You could also select linear, for example. The cubic interpolation has the advantage that all derivatives, higher order derivatives, are continuous, whether the linear interpolation, in that case, the second derivative is discontinuous. And because this topographies and other fields that you may map are used in the model to do computations, among which taking derivatives, you want to make sure that all the derivatives are continuous just to play it safe. So I'm going to execute this, and as I execute this, I'm going to put in front also this tick command, which is basically times the amount of time it takes for this interpolation to take place, tick-tock. We go here, I do that, and typically these interpolation could take a long time if the grids are very big. In this case it took only 4.9 seconds, which is pretty good. Now this array H, which comes here, is actually, if we look at size of H, we find that this has the same size of the grid because it's been interpolated, the topography has been interpolated to the grid. So we can plot that. We do mfig here. And now we can do RNT PLCM. We can put the grid and GRD to tell it, sorry, we can put H, which is the field that we want to plot, the two-dimensional field, and GRD, which is the grid, which contains all the information for the plotting package, like the longitude, the latitude, the coastlines. So I do that. And now suddenly you find that you've interpolated, you know, the raw topography onto your model grid. And so that's the first step. You can see that this is characterized by a shallow continental shelf here, which is very, very shallow here. And then, you know, you have a continental slope and then a deeper ocean. So now we have the bathymetry on the grid. Alternatively, you can, if we didn't want to use the Sandlin-Smith, we can use the eTopo. The procedure is just the same. You just execute this part of the script, and then in the end you do the grid data. And so I'm just going to do this very quickly. I'm just going to go here and do this. In this case, the interpolation of the eTopo 5 took less time because this is a coarser bathymetric data product. And again, I can do mfig again, and now plot, you know, the new topography, which is the eTopo 5, figure 3. So this is now the eTopo 5 that I just plotted, and I can compare that actually with the one from the satellite from Sandlin-Smith, which is this one. Okay, and I guess we should reduce the size of these a little bit so that we can compare them. And you can see that you know, they have some differences. The first difference is, for example, that that these mountain ranges in these eTopo 5 are shallower, are actually not as high as these. Okay, and then you can maybe see that there may be some more other regional differences, but more or less they kind of, you know, for the oceanic part, they track each other very well. So that's, you know, you can choose one or the other, and you can read about it, you know, in the scientific literature to see which one is best in your region, different topographies. Okay, so now